Hello, welcome to this session where we'll be talking about databases. I'm always happy to see people coming to database session in developer conferences, especially SQL databases, because I was quite surprised in the exhibition hall. I've seen most of the companies that are there about databases are all NoSQL companies. Seems that SQL is not yet popular again in developer conferences, but I hope that this will change. I'm Franck Pachot. I've been working with databases for more than 20 years. And of course, mostly traditional databases, a lot of Oracle, some Postgres, mostly as a consultant. And I changed a bit more than 1 year ago. When I was a consultant on traditional databases, I looked at the NoSQL databases, and I was quite interested by the scalability of it, but not really convinced by the lack of SQL features. And when I started to see those distributed SQL databases, which provide the same scalability as the NoSQL one, but with SQL features, then I was quite interested by that. And when I've seen YugabyteDB, because it was Postgres compatible, because it's fully open source, I was so interested that finally I'm now developer advocate for Yugabyte. When you like to use a product, better to be paid to use it. And here I will demo what is for me the most interesting thing in a distributed database, the scale out, of course, for elasticity and for resilience. And I will install it on Kubernetes. That's something I've seen a lot of applications deployed on Kubernetes, and the database was always a problem. Even if you can deploy Postgres on Kubernetes, you will still have one primary somewhere, and the other pods are just standby doing nothing. With distributed databases, then you can really be cloud native and scale with Kubernetes or any cloud solution. So that's the goal. I will show that on a managed Kubernetes on AWS, but basically that's nearly the same. And yeah, mostly I'm on Twitter, I blog. Do not hesitate to contact me on Twitter. I'm a lot there. And before the demo, I will just explain quickly what I will install. And do not hesitate to interrupt me if you have any question. I know in this room it may not be easy, but do not hesitate. And anyway, after the session, we can also discuss. So basically, I will install Yugabyte on Kubernetes with two stateful sets. I will explain why. So this is a cluster with 4 nodes, for example, and the idea of a distributed SQL database is that all the storage is local. You don't need a shared storage. You don't need NFS because the database will distribute the data, not the storage layer beyond it, and not the application above it. So basically, there are 2 stateful sets. The main one will distribute the data, but there is also one small one which holds the metadata of the cluster. Because basically, all nodes are equal. And you can add more nodes for distributing the data, but they need to know the cluster topology. They have some metadata in common, so that's something that will be stored in the master stateful set. And a production deployment will also not only distribute, but replicate for high availability. Basically, the typical deployment is on cloud with 3 availability zones. And if you distribute on the 3 availability zone, then the application, the database continues even if one is not accessible or fails. So for the master, you need only a small pod on each zone to be resilient. But where the data will be, the T server, T for tablet server. Tablet is the name of the shard, the part of the table, so a set of rows, a set of index entries that are distributed. So the tablet server is the stateful set that will scale with the workload, with the volume of data. And basically, they will have a persistent volume. And that's mostly what we will install. About the services on top of it, the service, we will have a load balancer on top of the master one. That's more for the administrative command, the cluster metadata. The application will connect to the T servers, and you can connect to any nodes. That's the point with distributed SQL databases. And Yugabyte is Postgres compatible in the sense where we really use Postgres. We plug Postgres on top of a distributed storage. And so that's the point. You have a service that will load balance to any T server, so any pod of the T server stateful set. No need for a proxy. Proxy just add latency. You can connect anywhere, so just at random to the different ones. Just a word about the setup particular to AWS here, as I will demo that. I said one stateful set for the master, one stateful set for the T server. Actually, I will deploy a different stateful set in each availability zone. The reason is that I want to be sure that the storage is attached to the same zone, and I want full control. With a database, we like to know where the data is. So better to have a stateful set in each availability zone, but they can communicate between each other. And the master will just have a pod, a replica on each one, and they communicate between each other. And I will show you everything that I will deploy. Basically, I will create a storage class. So I'm using a GP2 in AWS. I will create one for each zone. So I will deploy on Europe West. And on each zone, I will create a storage class to be sure that each node has its local storage. Of course, when you distribute, you don't want to have additional latency. So directly, let's go to the demo. Here, I have just an empty Kubernetes cluster on AWS EKS. And I will install. Let me check where we are. So I will install with a Helm chart that already exists there, that has the latest version here. And I just run a script that will install everything, and I will explain what it is doing while it is running. This script, I've scripted it just because I have those three stateful sets for the three availability zones. And we will look at it. Let me just change the size of all that. So here I've run, so you can see below, those are the commands that I'm running, copy-pasted on the other one. So I did a Helm show all Yugabyte, the Helm chart, and then I will show you the different parts that are important, the component, the image, so that's the YugabyteDB image. About the storage, so I have the master and the T server. Here I am looking at the default Helm chart. I will show later what I changed to be available on the availability zones. So about the storage, small thing for a lab. About the resources also, I don't put a lot just to save some credits in AWS. But you have the master, you have the T server, replicas. So that's the default Helm chart. The default is one stateful set will create 3 replicas. This is something that I will change. For example, for the master, as I will have 3 stateful sets for the 3 availability zone, I will have only 1 replica on each. I will show you the overrides that I'm doing there. G flags, those are the parameters passed when starting Yugabyte. Not really interested here for the moment. Just a word about the affinity rule. So here I don't use it because I deploy in different stateful sets. But of course, when you distribute, you don't want all pods at the same place, in the same node. and credential. I pass on that. And let's see the script that I'm running currently, so that it's running in the background. This is what I've run, where you see that I create, I created the storage class for each zone. I create a namespace, and this is the basic install. And the basic install with an override. And I will show you what I override for this typical installation. So that's the definition of the storage class, nothing special except the zone. And the override, I define as multi-AZ because I will deploy in multiple availability zone, and then I say in which AZ this one is. But all must know the other masters. This is how each node knows about each other. They all know where are the masters, and the master have the whole topology of the cluster. And then storage class for the master, for the T server. And in each availability zone, I need only one master. There is no need to scale that. It's just metadata of the cluster, control plane. The T server, I will start with 2. So 2 database nodes in each availability zones. What else interesting there? Resources, not a lot, yeah. And something important, when I start Yugabyte, I must tell it where it is in terms of zone, region, cloud, because the database will guarantee the distribution of data and the replication of data to be resilient in one failure. And then the database must know if the node runs in one availability zone or the other, and this is through those flags. Of course, you can deploy on premises, and you will use the same, but the zone may be a zone in your data center or a different data center. Those are just names so that it knows it. This is also used because it is a SQL database. The optimizer, the query planner, must know if data is far or not. So this is also used when there is a different alternative to get data from, better to get it from the same region, for example, to avoid latency. So this is what is running in the background. Let's check if it's done there. Yeah, perfect. Just checking that I have. We'll put that in the large one. So now let's check what we have. Get pods to see the pods that are there. I have large fonts, so I will remove everything that is system. I'm using VD data to show it as a table. If I do that, so you can see that I have a namespace per zone. I have a master and a T server on each one. And that's the only thing that is interesting there from the pods. And if I look at the services, I will also get that right there. The mouse is not working. That will not be easy, but I have a touch screen, so we will do that like this. So you can see that in each zone, let me just select the zone 1A, for example. I have a master in each zone, a load balancer, and so master UI, that will be where I connect the console to check the cluster. And I have the T server, so cluster IP, on top of it, a load balancer, because you can connect anywhere. And if you see the ports, I will connect with a Postgres client because it is Postgres compatible. And if I look at the load balancer, I can see the port. The mouse is back. 5433. The default for Postgres is 5432. We use 5433 here. So you can connect to any node with the Postgres protocol. Okay, and then we will have a look to the the web console that just shows the what is running, so the tables, the servers, and I have just a script that gets from the service the IP address, so this one. If you want to open it with your smartphone, I put it with a QR code, you will just see what is running, and I will show that in a browser. So that's a lab. I've opened everything publicly, and let's go to there. So the first page shows the masters. I have a master in 1A, 1B, 1C. Everything is replicated with the Raft protocol. The idea of the Raft protocol is that you have a leader and followers, and when you write always on the leader, and it waits for the quorum of the followers, so that if the leader is down, one of the followers can be the new leader. That's the idea of the Raft protocol, and this is why you see leader and follower. So this is a replication factor 3 cluster with 6 nodes. Remember, I've put 2 tablet server in each availability zone. I can see the tablet servers there. So 1A, I have the T server 01, and the same in 1B, the same in 1C. I have my 6 servers. For the moment, no activity. This shows the read and write. For the moment, I didn't run anything, and I will quickly run something and create a table to show you what happens when we add more pods, when we have a failure, all that. So first, because it is Postgres compatible, I will use a Postgres client. I define the Postgres environment variables for user. The host, I get it from the services. There is probably a better way to get it. I'm not an expert in Kubernetes. This is the way I automatically get the host and the port that are exposed by the service. Here I'm connecting to 1A there. Okay, so those are the credentials and the connection info for a Postgres client, and I will use PSQL, the Postgres client, to connect there, and I check the IP of my server. When you connect to Postgres, the IP of the server is the IP of the only primary node. Here it can be any one where you connect. And as the version, you see the Postgres compatibility version and the Yugabyte version. Because it uses Postgres, it's kind of, the query layer is stateless Postgres. So it has the Postgres endpoint, it creates the Postgres backend, it parses your query, it builds the execution plan, and execute it. And, but when it needs to read or write data, instead of reading or writing on local storage, then it communicates with the lower layer that is a distributed storage and transaction. We have also an additional view on the Postgres to see the other servers. So you can say that I'm connected to one node, it knows the other ones, 2 in each zone. Okay, just to prove you that I can connect anywhere, so I connect, just PSQL. I select the IP of the server where I'm connected, so that's the pods where I'm there through the load balancer. If I reconnect, there is a good chance that I have a different IP. So not a good chance, but let's connect again. Here I have one load balancer per availability zone, and only 2 servers per availability zone. So where I connect with this connection string, I can go to one or the other of those ones. So that's the distribution of the connection. When we say distributed database, it distributes the connection, it distributes the SQL execution, so all the compute, and it distributes also the data, the storage that is behind. Okay, now I will run some activity, and for that, I have a container that has a very simple Java program running some queries, and I define some use cases. This is the connect one that have multiple threads, 10 threads here, and connects and disconnects always, just to put some activity. If I look at the log, before the log, I will show you the connection properties. Maybe this doesn't start yet. Container not found, that's not really good. Did I really run it? Run, yeah, this one already exists, so it's there. Maybe it takes a bit of time because I have a very small Kubernetes cluster and I'm running 10 threads. Here we are. So that's I'm using the Hikari connection pool, and you can define the Postgres driver, but we have also forked the Postgres driver to be cluster aware. So the idea is that with only one endpoint, so you see multiple addresses, but it connects to the first one, so it connects to this one, and then it discovers the other one. That's the idea. You take an application written for Postgres, it has only one endpoint, and the first connection will discover the other one when it can connect, and the connection pool will distribute the connection. Okay, looking at the logs of that, I just connect and show where I am connected, and you see the 2 T servers that are behind the load balancer that I have there. Okay. I will run a few more things. The init one is creating a table and just putting a few rows on it. If I check the log, I can see the create table. Check the log again, I see the insert, so I have a table. And already, if I go to the grid there, if I look at the tables, I can see my table there. Replication info, each table has some replication info, which is 3 placement blocks here, one for each availability zones. And it has some tablets. Let me, so I have the structure of the table. By default, we are sharded on a hash on the ID, but that can be defined as a range also. And I can see the different tablets. So my table is, my table is hashed, is split by hash on the ID, and then I have multiple splits. When it grows, it can be auto-splitted to more tablets, and each tablet, so each shard, has raft, leader, and followers. So a tablet has multiple replicas, and because each tablet server knows the topology, it places the replicas, of course, in different availability zones. So you can see that this tablet, so that holds a few rows of the table, has its leader in zone 1C, a follower in 1B, another one in 1A. This one, the leader is in 1B. This one, the leader is in 1A. So this is how it is distributed. Of course, one row has its leader in only one place. This is a database that is SQL fully consistent. So you have only one place for one row, but it is distributed because different rows will be on different places. Okay, and yeah, we can check the logs. So those were the creation. I have a workload that just insert rows in there. If I check the log, I can see insert ongoing, and it displays from which node it is inserting. So not easy to see, but you see the multiple IPs. So inserts are write operations. So if you look at the tablet servers, you can see the write operations there that are mostly equal in all nodes, because all the data is distributed I insert with different value. There is a different hash value, and this is distributed. In SQL, when you insert, you do not only write, you also read, for example, to detect a duplicate key. Here you see only writes because those operations are the operation between the two layers, between Postgres and the distributed layer. The maintenance of the index, the checking of the foreign key, the unique key, this is done by the distributed layer. So insert are only writes there. You may wonder why there is 0 data there. Sorry. I have a timeout in the connection. I have data because I inserted data and it's persistent. The thing is that tables and indexes are stored in LSM trees, kind of RocksDB. Each shard is kind of a RocksDB database. And the first level of the LSM tree is a memory table to get fast for the fast ingest. And this is why you don't see a size of the file. The memory table is protected with redo, with write-ahead logging. So even if it fails, it's still there. But that's the reason why you see nothing really in the files. So it's still running. I'm just killing the display of the logs. And I run a few more things, which are probably a lot for my small server, but 100 threads doing some reads. If I check the logs, I can see what it is doing there. But to be sure, if I refresh there, I can see that I have also some reads operation. So that's about 1,000 read operation on each server. Everything is also distributed there. Okay, let's run a few more things. I have a count star. I have some delays to really have all kind of operations. And yeah, the count is just counting the rows and taking the difference just to show how many rows were inserted in the last minute. Okay, so that's what we can do from there. This is just like a normal database, except that multiple nodes, so multiple compute instance, multiple block storage are working to serve our database workload, and we connect to it as with a normal application. But the most important is that we can scale it. And more than that, we can scale, and to scale it, I will run only Kubernetes commands. I will run nothing on the database. The database will, let me do it while it's running and I explain. So I keep the logs on top so that we can see that it is running, and I scale each stateful set because I have each availability zones. You remember I had 2 replicas. I scaled that to 4. Just adding new nodes, and that's typically what you want to do if you have more activity, you are retail, it's Black Friday, you know that tomorrow you will have a lot, you want to add a lot of more nodes. You just scale. Kubernetes will create new pods. They will identify themselves to the master, and then the master will rebalance data, load, and the connections. The connection, because there is a load balancer there. So in my list of tablet server, remember I had 2, 0, and 1 for each availability zone. Now I have 0 in 1A, 2 in 1A, 3 in 1A, so I have 4 of them. I can see that some do not take yet reads and writes, the 3, but the 2 is one that I have just created and is already taking a few reads and writes. If I refresh, that's my browser. I don't know what I installed in the browser, but sometimes it fails. So you can see that now it starts to be more equal between the different servers. And let's look at the table. So if you remember, let me just go to there. I had different tablets, and each tablet had a leader in each availability zone on server 0 or 1, and now I expect that some of them will be moved to server 2 and 3. So I can see that. Server 2 is a new pod when I scaled, and has already a replica and even a leader. Same here, same here. Here, server 3 has a follower for this tablet. And I'm just checking, I was not fast enough, but during this operation, there is a point where we see an additional follower, because how Yugabyte does is that there is a new pod, it starts a new replica. The minimum is 3 because I'm replication factor 3, but to scale without interrupting the application, it just adds a new follower, and then when the follower catches up all the Raft logs about it, it can decide to remove the old followers, and then also decide to make it a leader to balance the leaders. Basically, when you read, you want consistent data, so you read from the leader. When you write, you write to the leader, and this waits for the quorum on it. So you want to balance the leader, because this is where most activity is done. We can also read from the followers if for reporting, for example, we accept some staleness, because followers, they answer to the quorum, so they are not consistent, but they are consistent if you read from the past seconds, for example. Okay. And this, of course, I'm inserting a lot of rows and counting everything, but you can see that the application, everything that was connected is still there, running. Nothing has changed. The election of a new leader takes 1 or 2 seconds, and the internal operation then is just retried internally, so you don't even get an error when you scale out. Now we will see what happens if we simulate a failure. Let me show, those were the inserts, so writes. And to simulate a failure, again, it's probably not the best way to do it. I will delete the pod in a loop, because of course Kubernetes will start it again. So that's a way to simulate a big failure. Only one availability zone, of course. In replication factor 3, if I have a failure on 2 availability zones, the database cannot continue because it cannot guarantee the quorum. With replication factor 3, we are resilient to 1 failure. And then, I didn't expect that to fail. Maybe it was just my log, I was connected to 1. But basically what happens in this case is that first, the failed server are detected as failed. Should refresh to see that. Where is 1A, 1A, 1B, 1C? I expected to see them still there, but that's not a big problem. Maybe I waited too much before looking at it. But what I see there is that they are still there. So didn't identify the name, but those containers are the ones that have that I'm constantly deleting. So what happened in this case? The pods where we had leaders, the database automatically has elected a new leader among the followers. But it keeps it as a follower just because usually those kind of availability zone failure are transient, a few seconds, a few minutes, and then you just keep it as a follower, and when it comes back, it still have the data and just have to catch up with the latest changes. By default, it stays like that for 15 minutes, so storing the Raft log for 15 minutes to be able to recover when it comes back. After 15 minutes, the idea is that it's a long failure, and then it will not be a follower anymore. It will create a new follower elsewhere and rebalance on that. But let's, for example, if I kill my loop running there, so the pods will come back again, and we will see that it will come back, and the follower will catch up, and then when everything is okay, leaders will be redistributed on it again. Okay, so basically the two main things here were showing that you can scale without any failure, without any error. And if you have a failure, so maybe I can explain, I have a few slides to explain what happens really when there is a failure. But first, do you have questions? If not, I will just show you how it behaves when there is a failure, because there are three cases. So here, I have the application connected to node 1. It's the Postgres backend running my query and reading or writing data depending on the row or the hash value of the row or of the index columns. It reads and writes to tablet leaders that can be anywhere on the cluster. Okay, and let's say that this one dies. That's the easiest case, because this one was not really interested, my session was not really interested by it at this current time, because it was reading and writing to the others and not connected there. So in this case, it's just that those leaders are considered as followers, and one of the followers will be elected. This is totally transparent to my session. Another case where what will fail is one where I'm currently reading or writing, so I need the leader there. Sorry, this was just when this one comes back, as I did there, it re-elects the leader there to rebalance. So this one fails, and this one I was currently reading or writing to one replica there. So what happens there, my session has to wait for the election of a new leader elsewhere. Because the writes wait for the quorum, we know that at least one follower has the latest value, the consistent. That takes 3 seconds. And again, it is a parameter. You don't want to elect a leader just because you have a few hundred millisecond latency in the network. So by default, after 3 seconds, there is a new leader election. The current operation is retried directly internally, and the application just sees an additional latency of a few seconds. Not all sessions, just the sessions that were currently reading or writing on this particular row. So the more nodes you have, independent of the replication factor, the more nodes you have, the less impact you have when one is down. And this is totally transparent. Third case, because you can connect anywhere, bad luck, you were connected to the pod that is down. And then, of course, there is no magic. The application will get an error. Usually in the application, you have a connection pool that can reconnect, and it will reconnect to another one. So that's the idea. It reconnects to another one. In the meantime, the leaders there were elected, became followers, and new leaders were elected, and everything continues there. But this, everything continues. The application got an error. If it was just running one small transaction like in AutoCommit, the database can rerun it, or the driver can rerun it. If you were running a long transaction, the database cannot decide to rerun your transaction because it doesn't know what the application did with that. And in this case, you need to implement a retry logic in your application. So those are the 3 cases of failure. The idea is that it's really managed automatically. Okay, do you have any question? Let me just check that my nodes came back. If I check here, so I'm again with 4 nodes per availability zone. This is the availability zone. The load, so everything is still running, so you still see the reads and writes running in the background. And my table has leaders and followers distributed. So replicated in all zones and distributed among the 4 servers that I have in each zone. Okay, do you have any question? Do you want to know more about anything that I didn't show there? I focused on the deployment on Kubernetes. I focused on the resilience and scalability. For the features, basically the idea is that it is fully compatible with Postgres. There are still a few things that doesn't really make sense in a distributed database, but compatibility with Postgres means that you can use the whole ecosystem of applications, frameworks, extension, all that. That's really a nice thing, and it is fully open source. Yeah?
You showed it was running against Postgres 11.
Yeah.
Later this year, 15 will come out. So how...
So currently, the compatibility version is 11. When Yugabyte started, they started with 10, and then they merged to 11 to see how difficult or easy it is to merge the new ones. And they decided to freeze that a bit because a lot of features were added. The plan is that at the end of the year, it is Postgres 13 compatible, and then following the versions. Following the latest, not like Amazon Aurora, where you can really decide which compatibility. The idea is to match the latest one. But that will follow. According to the engineers, it's not so difficult to merge it. I was really surprised by that. But even if there are different points in the code where it plugs the distributed storage, there are too many points to make it an extension, but it's still easy to identify it. And also the thing, we don't need to merge everything. For example, every improvement in vacuum in Postgres, we don't care. We don't have vacuum issues there. Improvement with indexes, we don't care because we store indexes differently. What we merge is really the SQL features. So yeah, the goal is to follow the compatibility. Yeah. Yeah. Yeah, I didn't mention one cool thing is that when you upgrade, you just upgrade node after node, rolling upgrade, and the application continues. That's also one goal in the high availability. High availability is not only about unplanned failure. High availability is also that you can have maintenance, upgrade the OS, upgrade the database, so that is fully supported to upgrade and downgrade only to the latest version in case something is bad in a rolling fashion. The only thing is that when you upgrade, the new features, most of the new features are not enabled until the whole cluster is upgraded. There was another question, yeah?
What happens if multiple application instances write to the same table and there is a conflict with their...
So about multiple application writing to the same data and there is a conflict, so the conflict is detected. And to be Postgres compatible, we have pessimistic and optimistic locking. We have all isolation level, read committed, and serializable. Usually, the users who build new application for a distributed database will run in serializable. Serializable means that you have no anomalies in race conditions, so that's really cool, but you may get an error where the application has to retry, which is okay if you build a new application in the spirit of a distributed database, but the compatibility is there also to be able to run something that has been written for Postgres and run it on Yugabyte. And the default isolation level of Postgres is read committed, which allows some anomalies, but has the big advantage that you never get a serialization error. It waits with pessimistic locking to resolve the solution. And then if the application is not built to retry in case of serializable error, then we use read committed and get it. Basically, the operation that goes from the Postgres layer to the distributed storage, the distributed storage is like a key value, a document data, a document store, which is transactional, fully ACID, but documents, and documents are table rows, index entries, or log information. So the same if you are in serializable and you read something, you need to put in the transaction intents in the provisional records that you have read this, and then if another one write it, then maybe there is a conflict. There is one question at the end. I think you will have to shout, but
You said that you can query either for reads, either the quorum or just one of the followers. Like, how would you make that distinction? Is the query different, or like how would you do that?
so the question is, you can query the followers. By default, it is a SQL database, fully consistent, so we read from the leader because this is where the latest change happened. What we do, the thing is that here I deployed on single region, multiple availability zone, where the latency, in AWS, you have 1 millisecond latency between availability zone. You don't see the difference between two servers in same availability zone or different availability zones, so that's fine. But this you can also deploy in multiple regions. And if you deploy in multiple regions, maybe you have some reporting that you do in Australia and you don't want the latency to go to Europe or US, especially for reporting. So the way you do that, first, it's only for read-only transaction. So you set read-only transaction with the Postgres command to do that. And you say with a parameter that you allow follower reads, which means that you can read from the followers. It is still consistent, but consistent as of a previous point in time. Basically, you define the staleness. It's kind of, I run a report, it's read-only, I accept a staleness of 30 seconds. And then it reads as of 30 seconds before, because everything is, all the rows are versions, it's MVCC like Postgres. So you read a previous state, but everything is consistent at this state. And the thing is, the followers know, they don't know if they have the latest change, but they know that they have the change in the latest seconds, because there are heartbeats every seconds. So this is the way you do follower reads, mostly for read-only reporting. There is also the possibility on top of that, so that is synchronous replication with quorum, but on top of that, between two clusters, you can also do asynchronous replication, and that's also a possibility when you have a cluster that is used mostly in Europe, for example, but you want each region to be able to have reporting without going to the region. This is used also for data governance. With the Postgres partitioning, you can partition the table. So imagine you are a bank, you have your customers, and you have a country code for each customer, and you partition on it. So you have a partition per country, and you want to put the European countries in a European region, and maybe not in an American company like AWS, maybe in OVH or something like that. So we do that with partitions, and we map the partitions to table spaces, and that again is a Postgres feature, except that in Postgres a table space is mapped to a file system. Here a table space will be mapped to a region, for example. So basically the sharding is there to distribute, and on top of it we can also decide the placement. And when you do geo-distribution, you probably want to decide about the placement, because you don't want a cross-Atlantic latency for each write, for example. So you want to set where are the leaders, or the leaders in preference. Like if one is down, then you accept additional latency. Okay, 1 minute left. Is there one more question? If not, I'm there at the conference and I will be happy. I'm developer advocate, so my goal is to talk about Yugabyte, but also get your feedback on how you use databases. If you look at new databases, distributed SQL databases, all feedback is good. And if you want to try it, it's fully open source. Okay, no more questions. Thank you very much.